For years, industrial safety programs relied on administrative rules and posters in the break room, assuming workers could be trained to avoid every danger. But human behavior is inconsistent under production pressure. True hazard mitigation requires a shift toward proactive physical engineering. Identifying the right solution requires accurate data. Relying solely on injury counts hides the productivity drains that impact a facility, such as lost supervisory time and the learning curve of replacement workers. These hidden costs must be tracked to be mitigated. This data table illustrates the DART metric, which stands for Days Away, Restricted, or Transferred. DART identifies workforce degradation by tracking restricted work activities and job transfers, rather than just severe accidents. It shows exactly how a facility loses its operational capacity. With this data, you can prioritize. Eliminating every risk is impossible, so managers triage hazards into 3 buckets: those that are physically infeasible to fix, those that are economically infeasible, and those that are both physically and economically feasible. This third category is where we target capital investment. True safety leadership is about resource allocation. By targeting the engineering budget toward feasible hazards that drag down productivity, managers maintain credibility and effectively deploy limited financial resources. Addressing those feasible hazards requires a hierarchy of control. Robust engineering fail-safes are prioritized because they physically remove the hazard, making them far more reliable than fragile psychological enforcement or rulebooks. This image shows a guard at the point of operation, the exact spot where a tool meets a workpiece. This is a high-risk zone for amputations. A transparent barrier provides physical isolation without sacrificing the visibility the operator needs to work. When you use sensors instead of barriers, you use the safety distance formula. You multiply 63 inches per second, the constant for human hand speed, by the time the machine takes to stop. This determines exactly how far away the sensor must be to stop the machine before a hand reaches the danger zone. Physical guarding only works during production. For maintenance, simply turning off a switch is insufficient because of stored kinetic or pneumatic energy. Workers use lockout-tagout protocols to bleed pressure and reach a zero mechanical state before they begin repairs. Engineering principles also apply to human ergonomics. The NIOSH lifting equation starts with a 51-pound baseline and reduces it using multipliers for variables like horizontal distance or torso twisting. This determines the recommended weight limit to prevent chronic musculoskeletal disorders. Whether you are guarding a mechanical press or calculating an ergonomic lift, safety engineering replaces unpredictable behavior with math and physical barriers. These barriers are vital in confined spaces, like silos and tanks. These environments are prone to atmospheres that are immediately dangerous to life or health, or IDLH. Because oxygen deficiency or toxic vapors can accumulate invisibly, these spaces require mandatory atmospheric testing before entry. Relying on a single closed valve is a fatal error. High-pressure lines suffer bleed-through, filling the workspace with toxic gas. The solution is a double block and bleed setup. 2 closed valves and an open bleeder vent leak safely away from the worker. Construction hazards involve similar hidden forces. Soil mechanics in trenches are unpredictable, and structural dynamic shock loads can snap rigging or collapse scaffolding. As seen in this photograph, these structural failures result in massive kinetic energy releases. Fire suppression also requires precise chemistry. You must match the suppression agent to the fire class. For example, gasoline requires a Class B agent, while energized electrical equipment requires Class C. Using the wrong agent can exacerbate the combustion. Pause and consider this. Before entering a mechanically driven silo that previously held flammable liquids, what are the 3 physical engineering steps and the specific fire extinguisher required? You need lockout-tagout or a zero mechanical state, a double block and bleed setup for isolation, an atmospheric test for IDLH hazards, and a Class B extinguisher. Surviving invisible hazards requires matching the specific hazard physics with an absolute engineering countermeasure. True hazard mitigation ignores guesswork, relying instead on a framework of physical laws and recorded data that functions regardless of the industrial sector. This framework rests on 4 pillars: tracking data through DART, prioritizing engineering over enforcement, calculating safety distances with math, and isolating energy through lockout-tagout. Mastering these protocols safeguards human capital, moving safety managers beyond the rulebook toward a structured architecture of hazard avoidance. The goal is to stop investigating human error after the fact and begin engineering a fail-safe environment from the start.